everyone did the homework. It's a difficult homework, and that's why we had TTAs giving you hints. And I don't know for what reason there wasn't a large showing. Okay, so I mean, I assume that this type of course will be difficult for electrical engineers. Yeah. You are mostly from the electrical engineering department, and for most of you, this type of course will be difficult. Okay? So I want to give you as much help as possible, okay? Because some of these concepts are confusing. Okay? So I think the exam is next week, okay? And the exam will cover until the lecture that I'm going to give this week. I'm going to be giving 3 lectures, okay, 3 extra lectures. Today I'm going to be talking about SRM, structured risk minimization, and a little bit of convex up, and then try to tie up everything that I've learned, that we learned. But I'm going to move on and talk about convex optimization. Optimization, because machine learning, at the end, it's going to be about optimization. Okay? So I'm going to go through that. But once I'm done with the lectures, I'm thinking of providing you with some review sessions. Okay? So either myself or the TAs will be going over the lectures that we've covered. Okay. Obviously, we can't do it for all the lectures, but we'll give you a review. Okay. So that's. I hope that's comforting. Okay. So, as I mentioned, this course will provide 4 homework sets. Okay. 4 homework sets. And 1 project. 3 or 4. 3 or 4. I haven't really decided. 3 or 4, and 1 project. Okay? And there will be a midterm. So midterm is next week. The project is going to be about reviewing papers that we've that's related to the topic that we covered. Okay? And I just want to remind you that the 3 topics that we'll be covering is, one is about learning theory, okay, PAC, agnostic, and epsilon, and SRM, ERM, that sort of thing. The second part will be about algorithms and convex optimization. And the third part will be about reinforcement learning. Okay? So this is what I said at the very beginning. Okay, learning, then some little bit of algorithm, and then reinforcement learning. Those are 3 my targets. So, and based on that, I'm going to, okay, so this is the project. Okay, so the project, this is uploaded. And what you're going to do, you read through this, you learned a lot of these things, and this project will try to provide students with opportunity to experience the use of the concepts that you learned, okay, by reviewing papers, okay, and also learn, state-of-the-art machine learning techniques. Okay, this project will encourage you to work in groups, but it's not a requirement. Okay. And the group size will be limited to 2. Okay, for 2 persons. And I have a format where you have to first pick a paper from either from learning theory, we've already picked some papers for you, optimization, and various papers for reinforcement learning. You make a choice, okay? You give me 3 or 4 papers, okay, in certain order, okay? And then we'll try to assign them. So 3 or 4 papers, and I want you to give me a proposal, 4-page proposal, okay? And I'll be talking about the proposal, okay? And the proposal has to be accepted by the course staff. That's me and the TAs. Okay? That's the first step. So I want, in the proposal, say, oh, I want to review this one, this one, this one, this one. Of the 4 papers, I'm going to review 1. Okay? But you have to rank them. Okay? And then you have to say what the paper is about and why you want to review those papers. We look at those proposals and we evaluate it, and we'll probably pick a paper for you. Okay? And we'll try to assign you a paper that you ranked as number 1. Okay? But if there's too many people who wants to review that paper, then we'll probably have to, move you to the second, your second preference or your third preference. Okay, once you've done that, then about sometime later, about a month later, you're going to present me with a video, 30-minute progress video, okay, detailing some of the things that you learned in the paper, okay? And then in finals week, you will have to make your presentation in front of the course staff. Okay? And you will be evaluated based on completeness, okay, clarity, and accuracy. Okay? These are the 3 criteria that we'll be evaluating. So these are the papers. Let's have a look at the papers. This is the deadline. Okay. Proposal, video, and final presentation. 30, 40% of your grades. Okay. And in the proposal, in the 4-page proposal that you present, clearly and concisely describe in mathematical terms, try to be mathematical as possible, of the problem or the statement that the paper is concerned. Okay? Maybe it's about an algorithm. Then what is the input, what is the output, what is it trying to do? Maybe it's a proof. Okay? What is it trying to prove? What is the significance of that? And maybe what steps are involved in the proof? Okay? If the paper is not proposing an algorithm but giving a proof about the theorem, please summarize the theorem and the significance of the theorem. Okay? If implementing an algorithm, you should prepare a slide clearly describing the input-output, I/O relationship, and separately describing the training and inference process. Okay? And if you're implementing, you would actually have to, write your own code and verify the performance that's stated in the paper. Okay? Describe any novelty and significant facts about the algorithm or the theorem. Okay? And you should include maybe, if there is a comparison between other algorithms, then you should do that. Okay? And also you have to, if you're working in groups, you have to tell me with the responsibilities of each of the members. Okay? Because I don't want a situation where it says, You know, one guy does all the work and the other guy is just for the ride. Okay? Clearly defining. And we're going to ask you questions. And then videos. Okay? This is a progress report. Each group submits a 30-minute progress report. Okay? And there is some software. Okay? That you can take videos of. Okay, so you make your slides, and from the slides you have, use that slide to present or the progress. Okay? And I would suggest that you put the text on the bottom of the video. Okay, that would be helpful because sometimes, you know, because we're not native speakers, we have accents, and if I misunderstand you, I may penalize you, okay? And you don't want to be penalized for your accent, because of your accent, right? So that's this. Please look at the software slides. It's not very difficult to use. And then finally, of course, you make your presentation and 6-page report. Okay? 20 minutes. So that's the project. Okay? So we selected the papers for you. Okay? So you have a choice of either doing something theoretical, okay? In that case, you're not doing any implementation. Or if you're doing something that's an algorithm, then you would have to actually write the code yourself and verify the experimental results. So that's that. Any questions? Any questions with this? Yeah.
So the main purpose of the project is to understand the paper and implement the algorithm in the paper and just analyze the result.
You'll be good, yes. That'll be it. But you may decide to do something theoretical. No? And there may be no experiments. So you just go through the proof. Because the learning theory that we've been talking about has been just mathematical proofs, right? So it's in that case, you may not need to implement an algorithm. Okay, so just go through the proof and talk about the significance of the theorem and so on. Okay.
So only the digits on the list will be allowed to.
Yes, yes, yes. So if this is what we've done. Okay. So please give me sort of a rank of your preference. Okay. So just don't give me just one paper. If you give me one paper and there's other people who have a very good proposal for that paper, and then you may not be assigned to that paper. In that case, then I'll just close my eyes and randomly choose one. It may be a very, I don't know, you may not like it. Okay, so give me a list of your preferences. Okay? Oops. Oh, okay, so this. So let's Okay, everyone's familiar with Rademacher and growth function? Okay. Simply put, Rademacher complexity is if you are given a random label, okay? Where is it? Oh no. A random label, okay, that's given by this Rademacher variable, okay, for n things. How is your hypothesis? How does that correlate with your hypothesis? Okay. How flexible is your loss function to correlate with this random number? And each one is either, you can take only plus or minus 1. So you want to make, so the Rademacher complexity is a random vector, it's plus or minus 1, and you want a G that correlates with that as best as possible. Growth function. You should also be familiar with growth function. Growth function is you're given data, x1 through xm, and what's the different possible functions or vectors, labeled vector, can you have over this data, x1 through xm? How many different possibilities? Should be familiar with this. And this is a function of n. So if I'm given m samples, what's the maximum number of different indexes I can have? Okay. And a VC dimension would be the maximum over all this growth function. Okay. So VC dimension, let's say the VC dimension is D, then what's the different number of functions or vectors I can have over these m samples? I'm given m samples. What's the different number of labels that I can have on these m samples if the VC dimension is D? Over, yeah. Okay. So you're given VC dimension is m. Oh no, let's just say I'm given m samples. VC dimension is D. What's the different number of labels I can have? It depends whether my m is less than or greater than. If the VC dimension is greater than the number of samples, then what is it? It depends. If I have VC dimension of 3, well, and I'm given 2 samples, then what's a different number of possibilities? What? 2 to the power m. Right? 2 to the power m. What happens if my sample is greater than D?
Limited to D.
Hmm?
Limited to D.
You will be limited to D, right? Exactly. Okay? So it will depend. Okay? So, see, the growth function, depending on the samples, 1 through, I don't know, whatever, infinity, and it's the number of possibilities of labels that you can put. Okay. And this one is looking at the maximum. And then there was all these proofs that you don't really have to go know exactly, but you can essentially put a bound on here the R stands for the risk. Okay, I could be using this L of H. That's H. Same thing. So this is the test error. This is the risk. Okay? The same thing. Test error and risk are the same thing, right? This is the empirical risk. It's the empirical risk. We found it. And there is this, we call this the confidence interval. And it's a function of here, DC dimension, and number of samples, and also the confidence, the confidence delta. So how would I write this thing in another way? How would I write this in another way? Probabilistically. What's an equivalent statement? Probability of RH minus R hat H, or using LDH, LDSH, that being less than epsilon, greater than, or greater than delta. I could write it this way. What is epsilon in this case? What is epsilon in this case? It's this term. That will be epsilon. Right? So I could state it this way or I state it this way. It's the same thing. Everyone understand this? Some of you were a little bit confused. Where did, I mean, we were talking about this. Where did you get that? Where did you get, this equivalent statements? Okay. This is epsilon. That's epsilon. So that's Rademacher. Okay, just want to introduce this concept, Rademacher. Okay, and based on this Rademacher, you can get something like this. Okay. So here again, what will be this minus that is something like that. Anyways. Okay. Now I want to talk about chapter 7. And SRM. Now I want to, and chapter 7 talks about non-uniform convergence. And I'll tell you what non-uniform convergence is in a little while. Non-uniform convergence. Non-uniform learning, actually. NUL. So let me just explain what this is. I have a hypothesis, okay, like ERM, but the hypothesis is a union of smaller hypotheses and these hypotheses are nested. So the hypothesis that I have a hypothesis. Like ERM, we have a hypothesis space. It's constructed as a union of hypotheses, smaller hypotheses, and these hypotheses are nested. So H1 is the smallest one. H2 is a superset of H1. H3 is a superset of H2, and so forth. It's nested this way. So you may say, well, what is this? Give me an example. Give me an example of a nested hypothesis. Polynomial of order 1, polynomial of order 2, polynomial over 3. Okay? It's nested. Or this works fairly well with polynomials. This SRM. It could be neural net with layer 2, layer 3, layer 4, layer 5, and so forth. Okay? So it's a nested hypothesis. Okay. In ERM, what we did was, regardless of whether the hypothesis was nested or not, you apply your training data and you found a hypothesis that did the best. Okay, that was ERM. Training loss, that minimized the training loss, that was ERM. In SRM, what we're going to do, we're going to look at ERM only for hypothesis nested in H1, okay, in a particular layer, I guess, or nest. So I look at all the hypotheses in H1, and I find one that minimizes the training error. Then, what I do is, in the loss, I add a complexity term that's related to H1. And obviously, as I go from here to there, H2 will be more complex than H1, and H3 will be more complex than H2. So this complexity term, as the n grows, the complexity term grows. And what you're going to do is penalize this one the smallest, this one a little bit more, and a little more. So as it becomes more complex, you're going to add a bigger complexity term to the loss term. And then you're going to choose, overall, what you want to choose is find a hypothesis that minimizes this term. One hypothesis that minimizes the sum of the training loss plus its complexity. So in this structure, you have hypotheses of different complexity. Okay? Not equal complexity, but different complexity. And you are penalizing it differently depending on the complexity. Okay? Everyone understand this? So here is a graph of the training error as you're going from this n. As n grows, the ERM is going to drop, obviously. As you use more complex model, the training error is going to go down. But your complexity term, that's represented by this blue line, is going to go up. And what you're going to look at is the summation of the training loss and the complexity term. That's the green thing here. Okay? So you want to be less complex, and you want to also minimize, you also want to have small training loss. Okay? This is structural risk minimization. Okay? That's the idea. And if you look at the algorithm just a little bit more in detail, so the hypotheses, all the hypotheses that I'm considering is a union of these subsets, sub-hypothesis spaces, okay? And these sub-hypothesis spaces are nested, and each one satisfies this uniform convergence property. Each one of them. What does it mean by having a uniform convergence property? What does this mean? It means that there is a sample complexity threshold, okay? If you're over that, then what? Then you can bound the test error with your sample error by some epsilon. Right? So each one of them has, each one of the sub hypothesis space has this property. And then there's this interesting part where you have to define a weight function. A weight function for each hypothesis, for each n here, there is a weight, okay, between a value between 0 and 1. And when you add up all the weights for each of the sub-hypotheses, it's going to be a value less than 1. So this is something new. So each H1, H2, H3 will have its own weight. this weight will be placed on the confidence, on delta. Okay? So your epsilon will be a function of sample and delta times this weight. Okay? So, and usually the weight, the smaller n is, the bigger the weight is. Okay? So, it's placing more confidence on hypotheses with smaller complexity. Now, the epsilon, so each sub-hypothesis satisfies the uniform convergence theorem, right? So you know that this is going to be a function of epsilon and delta, right? Epsilon and delta. And for each hypothesis, the epsilon is a function of, what was it a function of before? Epsilon was a function of what? Was a function of delta, was a function of what else? Sample. Okay? If you look, okay, epsilon will be a function of delta and sample. But here, it will be also a function of the hypothesis. And that's why it's called non-uniform learning. So as I said, epsilon n, is there a function of? Oh, here it is. Okay. Oh, this is, I don't have the equation right here. So epsilon, here was it it's not this one. It's not this one. It's okay. So let me just improvise. I'm not really. Okay, so this it's going to turn out. There has to be a Wn multiplied by delta. So, okay. So there is an epsilon, and the way you get this epsilon, you have to define this epsilon. It comes from. Sorry. It comes from, you set your epsilon from the number of samples and also from the delta and the n value of the nest. N is, so the hypothesis, which subset does it belong to? It's NH. So our hypothesis belongs to, is it H1, H2, or H3? Okay, so you're given training set, and you figure that out, and you find a hypothesis that minimizes this. So let me just say, I've said this before. What you do is, you find ERM here, of the hypothesis here, you calculate the complexity, okay? So you find the best hypotheses, meaning the hypothesis that minimizes the training error, and then you add on this complexity term. That will be representing H1. And then you find a hypothesis that's representing H2. Then you find also one that's representing H3. And then you compare. And you find one that minimizes this term. Okay? And that's how it's done. Everyone understand what I did? Okay? So you go in steps. Okay? You look at this, find the one that minimizes training error, and then you add on the complexity term. That's this term, representing of H1. Then you do that for H2 and H3, and then you figure out which of the representing hypotheses has the smallest loss plus complexity. And that will be your hypothesis that you choose. Okay? So, yeah.
Is there a case that n goes to
N goes to infinity here. N here usually goes for infinity. Okay. So you would stop at some point. I mean, obviously you can't go to infinity. So Wn, as I said, is the weight that, it's called the weight function. It's a weight you place on the delta. It's the weight that you place on the delta. And it represents the importance of each hypothesis. Okay? And usually, Wn is just used as this value or sometimes this. So when n is bigger, when you have a more complex hypothesis, then your weight goes down and your delta, your confidence goes down. Your delta goes down. And so forth. So your delta goes up, but your accuracy goes up. Okay? So everyone understand just the concept of SRM, okay? Having a nested, doing an ERM, and then adding some complexity term, penalizing the complexity. Okay? Obviously, you cannot compare the first order with the third order, because the third order will do much better in the training error. Right? Always. Which means that you should, what? Use infinite order. That's going to minimize the training error. Right? But is that going to generalize well? No. So this term right here penalizes the complexity. Everyone understand this? Okay. And this complexity term is the epsilon. Okay, it's epsilon. And SRM is non-uniform learning. Why is that non-uniform learning? Because the epsilon is dependent on the hypothesis. Okay? Before, the epsilon was just dependent on what? Sample and delta. But here, why is it dependent? How is it dependent on the hypotheses? How is it dependent? By the weights. But what does the? How is the weight? What is this a function of? Which subset does it belong to? Depending on the subset, your W is going to be different. So if my H belongs here, then it's going to have its own W. It's going to have a different W from the H that lives here. Okay? So that's why it's called non-uniform. Yeah.
I have a question.
Yeah.
So the motivation behind the algorithm called structure-based minimization
Yes.
is based on the belief that the generalization ability of a model is related to its complexity, right?
It's related.
To the complexity.
It's related to the training error
Yes.
and the complexity.
And how can we be sure that generalization is related to the complexity? Is it by observation or how? Maybe generalization is related to other kind of features as well,
Like for instance, what?
such as the sharpness of loss function or some method.
No, this is. I mean, there are many factors, like you said. This SRN just makes a distinction. Okay, so you can actually derive this SRN. I haven't done this. Okay. And the basic philosophy in machine learning is that simple algorithms perform better. So no, if you have algorithms that perform equally well on training data, okay? So for a given training data, you have many algorithms that perform equally well. Of the equally performing well algorithms, the one that is most simple will generalize. Okay? And so, if you remember the graph that I showed you in the very beginning of this course, I had complexity and the training error. This is the error. This is the foundation of machine learning, actually. The training error goes down this way. This is training error. But what about the test error? The test error is going to go like that. Okay? This was, okay, this is, and yeah, an Occam razor, It's a philosophy I mentioned in the very beginning of the class. Okay. Algorithms that perform similarly on training data that is, of the algorithms that perform similar on the training data, the one that is most simple will generalize better.
Is that correct by observation or is it theoretical?
You can actually do a theoretical proof on this based on various assumptions. And how do you define this complexity? It's not just number of parameters. One example is like you looked at the VC dimension of a linear function. You looked at the VC dimension of high order things. You looked at one for circles and so forth. You found that, okay, and I also mentioned that the VC dimension sort of represents the complexity. You looked at the sine, for instance, which had how many parameters? There's one parameter. But what is the VC dimension of that? Infinite. Okay? So VC dimension, complexity is not about number of parameters, but it's a very easy way to think about complexity. Okay? So how do you, so VC dimension was one of them. Rademacher was one of them. Okay? And there are other ways of representing the VC dimension. Okay? And representing the VC dimension in terms of the but SRM, in uniform learning, we had a fixed complexity. We were looking at fixed complexity. Okay? But in SRM, we are looking at hypotheses with different complexities. Okay, and it turns out, because I'm not going to prove this because this is also fairly long. It turns out that you could equate the sample complexity of a non-uniform learning like the SRM, which depends on three things: epsilon, this is sample, epsilon, delta, and hypotheses in this case. It is hypotheses. In the SRM, where does the hypotheses belong to? Which subset? And you can bound that sample complexity with the sample complexity of uniform convergence, which is a function of epsilons and deltas. So just by looking at this, the epsilon is half, and the delta, depending on what this is, the delta is also reduced. Okay, so you have better accuracy and confidence using non-uniform non-uniform. Okay. Any more questions? Okay, if there are no questions, I'm going to move on to convex optimization. So, we're given a training data. We've also chosen our hypotheses. The hypotheses. Let's say this hypothesis is it's a function of linear functions, and this hypothesis is a linear function, so it contains all linear functions with different gradient and y-intercept, and I'm going to represent that by theta, let's say, for instance. Okay? So it's this hypothesis is parametric. It's parametric. And we are also given a loss function. So it's y. These are defined. Okay. So this is the framework: training data. We have a hypothesis space, and we are also we've also defined a loss function. So what's the next step? We need to find out what theta is. Of some loss function plus maybe something. So we can say that all of this framework, this machine learning framework that I've mentioned, boils down to optimization. Minimizing, we call this, by the way, this is some objective function. Minimizing some objective. And very often what we would like is to have this objective function to be convex. And if it's not convex, then we can sort of approximate it as a convex function. And I'll explain why convexity will be important. Okay. So this is the framework. It turns out machine learning at the end is an optimization problem. So let me just talk about convexity first, and then convex optimization, and so forth. So first of all, let me define what a convex set is. A convex set is a set where you take a linear combination of 2 points in the set, and that linear combination is within that set. Okay? So for instance here, this is not a convex set because if you take a linear combination of these two, then this point is not in the set. This one is not convex. Here in this case, it's convex. You take any 2 points, it's within the set. So this is called a convex set. And we call this, by the way, any 2 points U, so this is U, this would be V, and if we take a linear combination like this where alpha is between 0 and 1, we call this convex combination. Okay, so depending on alpha, which is between 0 and 1, it's going to represent, this convex combination represents all the points between U and V. Okay? Convex combination. This is a convex set. Convex function. You're given a function, okay, and you take 2 points, okay, the argument U and V, look at the value, okay, and you take the convex combination of these 2 values, okay, linear convex combination of that 2 values, and if that lies above that function, then it's a convex function. So here, U and V, okay, the value, convex combination, okay, let's say alpha Fu plus 1 minus alpha Fv, okay, that would be that point. And I have to look at the corresponding point, which is equal convex combination of U and V, which is alpha U plus 1 minus alpha V. And then you look at the value of that point. If that value lies below the convex combination of these 2 points, then it's a convex function. And mathematically, you can write it this way. Function evaluated at the convex combination of 2 points is less than the convex combination of the function values. What's so nice about these convex functions? What is nice about these convex functions? It has one global minimum. Okay. So when we are minimizing, as I said, it's a machine learning framework, and then it turns into an optimization. It would be nice to have one solution, one unique solution, have a function that's looking like that. Another way of defining a convex function that relates with convex set is the epigraph. Here is a function, and you look at all points above that function. Okay? So all points here is represented by the yellow. If that yellow is a convex set, then this is a convex function. Is this a convex function? No. Because if you look at the yellow, if I take 2 points here and here, and I take the linear combination, these points do not lie here. So this is not a convex function. That's relating convex function to convex set. Okay? I'm going to skip over this. This is, I'm just going up ahead of going back to this. So it's going to look like arc min some function. Right? Usually this theta has to lie in some set. There is going to be a constraint on the theta. I can write this way. Or R min F theta x such that theta is in. Okay, I could write this. This is the same thing. You can have many, this can be written this way. Let's say theta is vector. Theta 1, theta 2. So it will be theta 1 has to be less than 5, theta 2 has to be greater than 2 point, it has to be, can't write it. So you're going to have, I can't write this. And so forth, theta k is between -2 and minus 4 and so forth. If you have a problem like this, and you want it to have a unique solution, it has to be convex. This has to be a convex optimization problem. When is this a convex optimization problem? This function has to be convex, and the set defined by these constraints has to be convex, set. Okay? Convex function and convex set. Then you have one unique solution. If you have a convex set, if you have a convex function and this set is not convex, then you may have multiple solutions. So it's okay, this is a proof. This is a nice property about convex set, convex function. It has one global minima, and so every local minima is global. very, very nice. Okay? Because usually in machine learning, in order to solve this convex optimization problem, we use gradient descent. You're going down the function, and you may reach a minimum, and you have to, how do you know if that minimum is global? You know it's global only when it's a convex function, convex set, right? So it's very important. It's a nice property to have. So it's not clear where, for convex function, all local minimums are global. Okay, so you have to prove this. If f is convex, then every local minimum, this is what we have to prove. Okay? And this is how the proof goes. Okay? I mean, this is probably obvious to you, but maybe once in your lifetime, you have to go through some proof like this to understand that this is true. So let's consider a ball. Okay? B stands for a ball. Okay? Around U. So it's all points that is distance r from U. And that's represented by V. Okay? B is all points, so centered around U and distance r away. Fu is a local minima of F. It's a local. Okay, let's just assume that U is the local minimum of U. If there exists an R such that for all V in this ball, we have Fv is greater than Fu. That's the definition of local minimum. Right? Everyone understand this? It's looking at the locally around you. And all the values are greater than Fu, so it's local minimum. It follows that any V that's not necessarily local, there is a small enough alpha such that you take the linear combination of U plus V minus U. What is this? What have I done? So I have U, and there's a ball, and the V that's outside, okay? And I've drawn a line, and I have my alpha such that this value is within the ball. Okay? Here it is. U, V, depending on alpha, I could be outside this ball or inside this ball. And when it's inside the ball, then you know that that's minimum, because that's the definition of local minimum. Right? So that's true. Now, if F is convex, you know that this is true. Oh, for the value of the linear combination of U and V, you can write it this way, right? Or the value at some point here, you can write it as linear combination of this way, can be written this way. This is just the definition of convexity, right? So here it is. It's some value, okay, so U and V, V is outside. I'm taking a convex combination of some point of, and I'm looking at the value of that F, which can be written this way. And if it can be written this way, then by convexity, you can write it this way, right? Now, we obtain that Fu, okay, so from this, we can see that, let's see, what was this? Now, rearranging this term, I can rearrange this term. We can write it in this way, right? Fu, moving it here. Let's see. Can I do that? Fu over Fu is. Wait a minute. I'm a little confused here. This value is that, and what? Oh, these things, yeah? Oh. Fu is less than this, but this is depending on some alpha value. For all alpha values. This is for some alpha value. So this is less than Fu. And if I rearrange this term, then Fu is that. But I had it so that alpha was some value. Golden alpha is it, So you understand this? Okay, so the way it is, if this is true, then Fu, this is less than. So that is Fu, which gives you that. Then rearranging this term, alpha Fu is going to be less than alpha Fv, and alpha and alpha, so we get that. But the way I've defined it here is there's a small enough alpha. Okay, so for some alpha, this is true, and you get that. I guess it doesn't have to be. If you just find one alpha, that's okay. This is true, right? You have U and V for certain alpha very small, then you know that Fu is that. Okay. This comes from convexity. Okay. Then for certain alpha Fu, you can, this term is going to be greater than this term, and then rearranging it, you get that, and then finally you get that. Which means that the local minima is global. Okay. Another definition that's very important for convexity is this. This is for a convex function. If f is convex and differentiable, then this is true. What is this? I have a function. I look at its value, Fu. That value is going to be greater than the tangent that you drew at another point. So at W, I drew a tangent, okay, which is this equation right here. Why is this? So here it says U minus W is this direction. Then, and the gradient is that. Okay. So this represents, for this, how much is it going to go up? And then you're taking an inner dot product with how much you're going on this side. So it's telling you this is saying how much you are going to go up. Right? So from FW, I'm adding this much. And that value, if that value is less than the value of the function, then this is a convex function. I don't know if I explained it very well. Okay. So this is the gradient, which is going in the x direction, how much you're going to go up, right? It tells you how much you're going to go up for how much x value you're going, and this is how much value you're going on the x direction. So this is telling you how much you're going to go up in the y direction. And then you add that on to FW, and it's still smaller than the value of the function. Okay. This is another definition of convex function which will become useful. Now, another very important concept, let me just do this one and done. So, the function that, I'm already giving you why our objective. Machine learning, really, it's going to boil down to minimizing, finding the argument that minimizes this f function, and this theta is in this space. Okay? But this function, and we're going to be using, and the algorithm to do this is this. This is what we're going to be using. To minimize this, we're going to be using this gradient descent. It works for this, works for even a function that's not convex. It's just looking at the current value and going in the opposite direction of the gradient of this. And that's how you keep on updating. Okay? What is this function usually? What does it represent in machine learning? What is it?
Loss.
It's the loss function plus some other junk. Maybe regularizer and various things. This loss function may not be what? Huh? May not be convex, and it may not be differentiable. What happens if you cannot differentiate? Huh? No. You use the concept subgradient. Okay? This becomes the subgradient. So let me explain what subgradient is very quickly. Okay? So V is a subgradient of F if this is true. Okay? So what has changed from the other definition? I had what? I had Fu greater than Fw plus gradient of F U minus W. Right? Instead of this is v. Any vector satisfying this will be a subgradient. Okay? So, let's look at this function. Certainly it's not differentiable right here. It's not differentiable because it's got two gradients, right here and one right here. If I'm going from this way, it's this gradient. If I'm going from that way, it's that gradient right there. Okay? Following this, what is the subgradient here? It's all V. These dotted lines represent V. All these V's, and if I take it with, and I take the inner dot product with UWV, it's going to be what? It's going to be below. It's going to be below this function. So in this picture, there are infinite number of subgradients. And you can choose any. And what subgradient will be the easiest to use? Will be this one. This is gradient 0. Okay? So that's subgradient. Differentiable set is a set of all the subgradients. Differentiable set. Okay? If F is a convex set, then if and only if for every W, the differentiable set is not empty. Okay, now let's look at this. What is the subgradient of here? What is the subgradient? How many subgradients are there for this continuous function? It's just the gradient. There's only one. There's only one. If it's differentiable, there's only one in the differentiable set. What about if I had a function like this, looking like this? Obviously, a function like this, the differentiable set does not exist everywhere. Okay? This has to be true for, so if I take this subgradient at some point at W, okay, subgradient at some point at this W, this has to be true for all U, for all values of U. So actually, maybe this will be a better notation to use. So this gradient descent is subgradient descent. So this is it's 4. I'm over my time. So I'm done here, and I'll see you Wednesday. I'm thinking of having one very short homework regarding this convex. I don't know whether very short ones to help you with your exam. Is that good? Okay. So I'll have one prepared by Wednesday evening. Okay? Very short homework.